Hello, welcome back to the lecture series in wave optics. In last few lectures we have discussed Fresnel diffraction, in which we considered the spherical or cylindrical wavefront were incidenting on the diffracting aperture or a diffracting edge. We are very well known that to observe a diffraction pattern we required a source of light, a screen and or a telescope through which we can view the image, and a diffraction device or an aperture from which the diffraction taking place or the bending of light taking place. To consider the different kind of diffractions, we assume the position of the diffraction position of the source of light or screen or the telescope with respect to the diffracting device and the nature of the incident and diffracted wavefronts. So, in last lecture we consider the wavefront either the cylindrical or spherical that is incidenting on the diffracting aperture. That was the Fresnel class of diffraction. Now, today we will discuss the Fraunhofer type of diffraction. Here the Fraunhofer diffraction we consider a plane wavefront is incidenting on the diffracting aperture. In when we compare with the Fresnel diffraction, in which the cylindrical or spherical type of wavefront were incidenting, and the plane wavefront is incidenting on the diffracting aperture, and for that we keep the source or source is placed at infinity, and an infinite source that sent a plane wavefront that is very familiar with us. And if the source is very close, we may use the convex lens with the source kept at the focus, so that what happens, we will be getting the parallel beam of light. Therefore, that parallel beam of light will that is an equivalent to the plane wavefront. Let us discuss a few differences between Fresnel class and Fraunhofer class diffraction. Here you can see the left hand side we have the Fraunhofer diffraction, and to compare we have the Fresnel diffraction on the right hand side. So, in Fraunhofer diffraction, a source of light and a screen which are kept at infinite distance from the diffracting device or from the aperture. In that case, in Fresnel class diffraction, the source and the screens are at place at a finite distance, so that we will be getting either the cylindrical wavefront or a spherical wavefront. Again, then the incident wavefront is a plane wavefront in case of Fraunhofer diffraction, and in Fresnel we will have cylindrical or spherical wavefront, and the diffracted light is collected by a convex lens in case of Fraunhofer diffraction. There is no lens we are using in Fresnel diffraction. The center of the diffraction pattern is always the bright in case of Fraunhofer, and in case of Fresnel diffraction the center of diffraction pattern may be dark or bright depending upon the number of Fresnel zone we constructed in the wavefront. And we may use this Fraunhofer diffraction and in case of a single slit or a double slit or a grating arrangement in which we use large number of slits large number of parallel slit in case of grating, and this Fresnel zone Fresnel diffraction pattern we can observe by using a Fresnel zone plate, which is used to get the diffraction pattern in case of Fresnel class diffraction. Now, we will discuss the diffraction at a single slit, that is our point of discussion. Now, let us consider the arrangement as shown in figure. This is the we are considering the Fraunhofer diffraction by a single slit. Now, you know that a slit is a rectangular aperture whose length is large compared to its breadth. So, we are considering AB as the slit, and we are considering this slit is perpendicular to the screen. We are considering a rectangular slit which is perpendicular to the screen. Now, let a monochromatic light is incidenting. How this monochromatic light is incidenting here? We are using a source S. Now, this source S is sending either cylindrical or spherical wavefront which is passing through this lens. Now when it is passing through lens, this will be sending a parallel beam of light that is equivalent to the plane wavefront. Therefore a plane wavefront is incidenting on slit AB. So this is, we are assuming this is a monochromatic light, yeah. Now this light is incidenting on slit AB, and here we are taking this E as slit width, and we can consider a few light waves which are diffracting by an angle theta here. Now another convex lens we are placing in front of the slit. That lens placed in front of the slit is focusing the diffracted light beam on the screen, on the screen. According to the consideration of geometrical optics, a sharp image of the slit is expected to form at the center point O. In the screen we will see a pattern of a bright and dark bands, and in which, so in this case what happens, supposed to be the light is incidenting on the plane wavefront is incidenting on the slit AB, and those light without any deviation will be focusing at the point O. Therefore we are getting a central maxima, and at the central maxima we will be getting a maximum intensity, and you look at the plot of the intensity profile, and at the center this intensity is maximum, and either side of that central maxima we can observe an intensity distribution in which we have minimas and a few another maximas with a smaller intensity. These are called the secondary maxima, and this type of pattern we just called it as diffraction, Fraunhofer diffraction pattern. And you look at the graph how the Fraunhofer diffraction pattern, in which we have maxima, minima, then these are the secondary maxima in both sides. We can use a method that would be more useful in understanding the physics behind the formation of this type of interference pattern, and to derive the further into use in derivation of the further cases. Here we assume every point on the wavefront striking on the slit AB will break into many parts. For example, just we are assuming here it is a plane wavefront, then the plane wavefront is incidenting on slit AB. Now this plane wavefront we are dividing into many parts. Each point in the slit, or each part in the slit, each part in the wavefront incidenting on the slit AB will act as the source of secondary wavelets, and all the point on AB are in the same phase, you remember. Hence the point source will be and all the point will be in the coherent source. Now this will be spreading out to the right in the all direction to the screen. Now from here the wave is spreading towards the screen through the lens, and a central pattern, central maxima is formed at on the screen on the point O, that is called the central maxima. The point on both sides of central maxima on the screen will have either maxima or minima depending upon the path difference between the two superposing waves at that particular point. Now we will discuss what is the mathematical explanation for that intensity distribution on the screen. We will try to reach a formula or an equation through which the mathematical derivation using a vector addition of the amplitude of many superposing wavefront in this particular case. So considering infinite point of secondary wavelets between A and B, here the slit, so the wavefront is incidenting, we are considering infinite point sources over here. Now initially let us consider what is the path difference between the wavefront from A and B. So this A and B is the extreme point of that slit. Now we have to calculate the path difference here. So the path, in order to calculate the path difference, let us draw a normal to the point B, and here this is angle is theta, sorry 90 degree. See at the point C we will have the 90 degree. So, the path difference between these two wave path from this particular point and from this particular point, these are equal in reaching point P on the screen. So, it is obviously the path difference is BC. Now, the path difference BC can be identified by calculated by considering the triangle ABC here. So, you know this triangle ABC is a rectangular triangle, therefore, you can easily calculate the path difference BC by considering the angle over here. Here theta is the angle of diffraction in which we consider here. So, sin theta can be equal to the opposite side by adjacent side, that is the slit width AB. Therefore, the path difference BC can be written as AB into sin theta, and AB is nothing but the slit width E. Therefore, we will have the equation E sin theta, and if we have the path difference, it is quite easy to calculate the phase difference delta. Now, the delta is equal to 2 pi by lambda into path difference, that will be 2 pi by lambda into E sin theta. Now, if the slit is divided into n equal parts, we are considering this slit is considering to split into n equal number of parts. So, the phase difference between two adjacent waves from two adjacent part delta can be written as 2 pi by lambda into 1 by n into E sin theta. So, this was the total path difference we have estimated between the two extreme point. So, now we are considering the phase difference between two adjacent part, right. So, that will be 2 pi by lambda into 1 by n into E sin theta. Now, how the formation of maxima and minima can be explained through a vector method. Now, we consider here the slit is divided into n number of parts. Now, each part is sending secondary wave front. Now, that each secondary wave front has certain amplitude. Now, that amplitude I am drawing here as this diagram. Supposed to be the amplitude from the first part is m into p. MP is the amplitude from the first part, that I am taking it as A. A is the amplitude from the first part. Similarly, we have the second part, the wave front sending from the second part, but the second part will be sending the wave of same amplitude, but there will be a phase difference of 2 pi by lambda into 1 by n E sin theta, as we have discussed earlier. So, there will be a small phase angle between the wave from first part and the second part. So, P1 P2 is the amplitude from the second part, but there will be a phase difference. The angle here, it is not theta, the angle here we have considered as delta. Now, P1 P2 will be making another vector, the amplitude here, this will be making the third amplitude. There will be an angle between P1 P2 and angle between P1 P2 vector and P2 P3 vector, again the angle will be delta itself. So, you add all the vector that is incidenting at all the vector, you will be getting a resultant vector as MPN. That MPN will be the resultant vector, that means the resultant amplitude at the point P here. Therefore, here we are considering r theta as the resultant amplitude here. Now, we are considering some geometrical consideration here. First of all, we are considering a triangle here, it is MP1. This is a triangle, and I am just drawing a normal to the center here, and this we will be getting at this point I am considering it as x, and you remember there is an angle between first wave and second wave, that is delta. So, half of that angle we can consider it as delta by 2. So, from the first triangle MXC, from the triangle MXC we can consider as sin delta by 2 is equal to mx by c, that is opposite side by hypotenuse itself. Again this mx can be written as mc into sin delta by 2, and you remember mx is nothing but the half of the amplitude, therefore this is a by 2, mx the distance is a by 2, therefore I am writing it as mc sin delta by 2 is a by 2. Similarly, we can consider this particular triangle, this center point M and P1. So I am considering that particular triangle, and that triangle, just from that triangle I am just drawing a normal line to this particular vector, and that point supposed to be meeting at point y, and this angle is 90 degree right now. We have then another right angle triangle. So from that right angle triangle we are considering sin n delta by 2. How this sin n delta by 2? So you remember there is the angle between two vector, it is delta. So we have n number of angles here, so total angle here it shall be n delta. So but now we are taking this particular angle, this is half of that total one, therefore we will have this particular angle as n delta by 2. So we have my by mc is equal to sin n delta by 2. So from this equation we can have my is equal to mc into sin n delta by 2, where this will be giving you this particular my, that will be giving you the half of the resultant wave, that means r theta by 2. So therefore I am writing it as r theta by 2 here. Now these two equations, equation number 1 and equation number 2, just I am dividing as 2 by 1. So if I am dividing it as 2 by 1, so this will be r theta divided by 2 divided by a by 2 from the left hand side, and on right hand side we will have mc sin n delta by 2 divided by mc sin delta by 2. Here mc and mc will be getting cancelled out, then we will have 2 and 2 will be getting cancelled out, a coming this way, and so therefore the resultant amplitude r theta is equal to a into sin n delta by 2 divided by sin delta by 2. Well, here we know what is the value of delta. The delta is 2 pi by lambda into 1 by n into e sin theta, we have already been derived in this session. So I am just substituting the value of delta here. So r theta is equal to a into sin n by 2 into, I substituted the value of delta here, and again dividing by sin theta by 2, sorry sin delta by 2, and here I am sin 1 by 2 into substituting the value of delta 1 by n into 2 pi by lambda into e sin theta. So let us cancel out whatever the factor we can do here. So we will have 1 by n and 2 will be getting cancelled out here also, here n cannot be cancelled. Here 2 and 2 will be getting cancelled out. So we can have the formula as a into sin pi e sin theta divided by lambda divided by sin pi e sin theta divided by n lambda. Yeah, this was the formula we have derived, and pi e sin theta divided by lambda I am just substituting it as alpha. So I can have this formula as sin r theta is equal to a into sin alpha divided by sin alpha by n. When you here we are considering n, small n is the number of the parts we have assumed in the number of the parts we have consider in the wavefront which is incidenting on the single slit, that we are considering large number of parts here. Therefore obviously this n is very greater than alpha. Therefore sin alpha divided by n is a alpha divided by n shall be a very small term. Therefore you can write sin alpha by n is approximately equal to alpha by n, and therefore this formula, in this formula I can write a into sin alpha divided by simply alpha n. So rearranging this formula, I am taking this n here, therefore I will have the resultant amplitude as r theta is equal to n into a into sin alpha divided by alpha. Now when r theta is equal to this, so this is the equation for the resultant amplitude. So when theta is equal to 0, so we can have, let us take an r theta becomes r of 0, that will be n into alpha sin alpha divided by alpha when theta is equal to 0. When theta is equal to 0, alpha obviously becomes 0, you can apply the limit alpha tends to 0. Therefore sin alpha by divided by alpha when alpha tends to 0 becomes 1. Therefore this r0 can be written as n into a. Now you just we can just simplifying this particular formula, you can write this r theta as instead of n into a, I can write r0 into sin alpha divided by alpha. So this shall be the final formula for the resultant amplitude. Now we are very familiar that the intensity is directly proportional to the square of the amplitude. So the intensity I is directly proportional to square of the amplitude r square, and I is can be simply written as a constant into r square. So I have this formula for the intensity as k into r0 square into sin alpha by alpha all square. Right, again let me find this k r square, I am just taking it as I0 by considering theta is equal to 0. Then therefore I will have the intensity I is equal to I0 into sin alpha divided by alpha whole square. So this is the equation for the resultant intensity due to the diffraction from the single slit. So we will be getting an intensity distribution on the screen as I is equal to I0 into sin square alpha divided by alpha square. Yeah, we see on the screen that we can have a central maxima with alternate bright and dark regions. So the intensity distribution curve we will have like that only, we will have that we will have a central maxima at the center, and then in both sides of the central maxima we can have the secondary maximas and minimas. So what is the condition for the principal or a central maxima in the case? So we know that the resultant amplitude is I is equal to I0 sin square alpha divided by alpha, and when the intensity becomes maximum, this intensity becomes maximum as we have discussed earlier, we can have let us consider the theta is equal to 0. So when we consider the theta is equal to 0, you know that alpha is directly proportional to sin theta, therefore alpha also tends to 0. So when alpha tends to 0, you can have the limit application, limit alpha tends to 0, then sin alpha divided by alpha becomes 1. So this is a very well known formula in mathematics. Therefore in this particular case, when alpha tends to 0, when or alpha is equal to 0 or theta is equal to 0, we can have intensity I is equal to I0. Therefore I0 is the position of the intensity of the central maxima. So this is how the entire picture here, source which is plane wavefront incidenting on the slit, and at the central point we will be getting the central maxima, and the central maxima it just look like this. You see this is the width of the central maxima, and the central maxima on the real screen you can visible, or through a telescope you can visible like you can view like this, and then we can have the second minimas, then we have the maxima with a smaller intensity. You see how this look in a real view. Here it is the intensity, but here it is very smaller in comparison with the central maxima. In both sides of the central maxima we can observe the secondary maxima, right. Well then this was the condition we have derived for the central maxima or principal maxima. Here for the condition theta is equal to 0, here this is happening when the path difference E sin theta is equal to 0. So, at the point at the center point O. So, this is how you can this is visible here. So, here when we consider this point O, this is the point of central maxima. So, both rays from A and B, or you can say the entire upper part and the lower part. So, the light from upper part and the light wavefront from the lower part will have the same path to reach at point O. Therefore, the path difference E sin theta, that was 0 for the central maxima or principal maxima in case of diffraction at a single slit. So, with this I am summarizing this session here. We have discussed the Fraunhofer diffraction at single slit and derived the equation for the resultant intensity due to the diffraction from the single slit, and we will continue this topic in the next lecture, and we will meet again in the next session. Thank you.